Hello and welcome to this video tutorial on understanding DBSCAN, density-based spatial clustering of applications with noise. I am Jyoti Bhattacharya, a Master of AI student at MAN in my second semester, and I'm submitting this video tutorial as part of my coursework for COM 6915 Machine Learning. And this is me. So without further ado, let's get started. DBSCAN is a versatile clustering algorithm with applications across various domains, including data mining, machine learning, spatial analysis, and image processing. Its ability to handle noisy data, identify clusters of arbitrary shapes, and automatically determine cluster density makes it a valuable tool for exploratory data analysis. So basically, it has an amazing power to identify clusters from even among noisy data. But how does it do that? Well, to understand, we first need to talk about its inner workings, and first up, its inductive bias. DBSCAN's inductive bias is primarily shaped by its reliance on the concepts of density and proximity in deep space, or commonly known as a feature space. So DBSCAN assumes that clusters in data are areas of high density separated by areas of low density. This assumption is crucial because DBSCAN identifies clusters based on density points rather than assuming specific geometric shapes for the clusters. Proximity-based connectivity. DBSCAN defines clusters as regions of data points connected to each other by specified distance threshold, often referred to as epsilon. This assumption implies that points within a cluster are closely located in the feature space and which can be reached from one another through a series of neighboring points. And number 3, noise tolerance. DBSCAN distinguishes between core points, border points, and noise points based on their density and connectivity. Overall, these assumptions guide DBSCAN's clustering process and influence its performance in identifying meaningful patterns in the data space. Now that we know about the inductive biases of DBSCAN, we can move on to the assumptions that DBSCAN algorithm takes into consideration. Basically, the inductive bias of DBSCAN hints quite well at the assumptions that it makes under the hood. DBSCAN has few key assumptions, like number 1, density-based clusters, where DBSCAN assumes that clusters in data are regions of high density separated by regions of low density. Connectivity via proximity. DBSCAN assumes that these points belonging to the same cluster are closely located in the feature space and can be reached from one to another through a series of neighboring points. This notion of proximity-based connectivity forms the basis of how DBSCAN defines clusters. Number 3, uniform density within clusters. DBSCAN assumes that the points within a cluster have similar densities, meaning that they are uniformly distributed within the cluster. And number 4, tolerance for noise. DBSCAN assumes that the dataset may contain noise, which refers to outliers or data points that do not belong to any specific cluster. Overall, DBSCAN's assumptions are integral to how DBSCAN operates and underlie its effectiveness in handling a wide range of datasets. Now that we have discussed about the inductive bias and the assumptions of our algorithm, so let's discuss about its workings in detail and basically the amazing algorithm behind it. Basically, the algorithm has 8 parts, and we will be looking into it with an example of very simple data, like so. Number 1, initialization. The DBSCAN algorithm begins by selecting an unvisited data point randomly. This point is labeled as visited and its neighborhood is explored to determine its density. Number 2, density determination. For each visited data point, DBSCAN calculates the number of neighboring points within a specified cluster, often determined as epsilon. These neighboring points form the data point's epsilon neighborhood. Now, number 3, core point identification. A data point is classified as a core point if the number of points within its epsilon neighborhood exceeds a predefined minimum threshold, often denoted by min points. Core points are indicative of regions of high density in the data space. Cluster expansion. Once core points are identified, DBSCAN begins to expand clusters by recursively adding neighboring points to the cluster. If a neighboring point is also a core point, its epsilon neighborhood is explored and the process is continued recursively until no more core points are found. Number 5, border point assignment. If a data point is not a core point but lies within the epsilon neighborhood of its core point, it is classified as a border point. Border points are considered part of the cluster but do not initiate cluster expansion themselves. Now, number 6, noise point identification. Data points that are neither core points nor border points are classified as noise points. These points do not belong to any specific cluster and are considered as outliers, which are presented in the picture as red points. Number 7, cluster formation. As the algorithm iterates through the data points and begins to form clusters around the core points, expanding to include border points within their epsilon neighborhood, each cluster consists of a set of core points interconnected through density-based connectivity. Number 8, termination. The DBSCAN algorithm terminates once all the data points have been visited and assigned to clusters, classified as noise points, or remain unvisited. At this point, the algorithm outputs the identified clusters along with any noise points. So quite a lot of steps, but to sum it up, for each data point, its neighborhood within a fixed radius epsilon is determined. If a point has at least a certain number of min points, including itself, it is considered a core point. Then the cluster is added by recursively adding neighboring points to the cluster until no more points can be added. This process is repeated for the remaining unvisited points until all points are assigned to a cluster or marked as noise. So to understand it, let's take a very simple visualization and let's hop on to Google Colab for that. So here you can see that we have the initial data that I have plotted from like 300 samples random data, and here we can see the data. Now using the DBSCAN algorithm, we can set the epsilon and the min samples to some size, which actually clusters the data quite well. And we can see these are the noise points that are present in purple. And by changing the epsilon and mean samples, we can see how it affects the data. Increasing epsilon makes the data like this, which is pretty self-explanatory after we have gone through the algorithm. And you can see the various details, that various effects that it can have, so we can always play with the data just to make sure which actually works for us, because epsilon and min samples are basically the hyperparameters that we have to train. Now moving back, we can also see that this is a pretty live demonstration, although this is quite slowed down in real time. But this is actually what DBSCAN is doing under the hood by basically trying to identify all the core points, expanding to it, and then identifying any of the border points, then moving on to the next cluster and repeating the process. So it identifies the noise and then moves forward. Now moving on to one of the important aspects of machine learning algorithm, that is hyperparameters. Now, as I have already explained, there are two hyperparameters that we need to actually tune properly. Those are the epsilon and the mean points. Now, epsilon is basically the radius parameter which defines the maximum distance between 2 points for them to be considered as neighbors. It determines the size of the neighborhood around each data point that is used to assess its density. A smaller epsilon value results in tighter clusters, whereas a larger epsilon value may merge nearby clusters into larger ones. And number two, mean points, specifies basically the number of points required to form a dense region, also known as a core point. A data point is considered a core point if it has at least mean points number of neighboring points within its epsilon neighborhood, including itself. Increasing the mean points leads to a denser cluster and may help filter out noise points. However, setting mean points too high may result in smaller clusters or even prevent the algorithm from identifying any other clusters. Now, there are three other optional ones that are important to discuss if we want to tweak the model a bit. So distance metric, which basically specifies distance do we want to use, for example, Manhattan distance, Euclidean distance, or maybe the Mahalanobis distance. Number four, the algorithm, which basically that which algorithm we can choose to classify the nearest neighbors, maybe the ball tree, the KD tree, etc. And number five, the leaf size, which specifies the number of points in each leaf node of the tree. So overall, tuning these hyperparameters appropriately is essential for achieving the optimal clustering results with DBSCAN. So now that we know how DBSCAN works, let's explore the relationship to other ML approaches in more detail. Number one, K-means clustering. K-means is one of the most widely used clustering algorithms. Unlike DBSCAN, which is density-based, K-means partitions data points into a predetermined number of clusters based on their proximity to cluster centroids. While K-means is effective for spherical clusters and works well with large dataset, it requires the number of clusters, K, to be specified in advance, which may not always be intuitive. DBSCAN, on the other hand, automatically determines the number of clusters based on the data's density and does not assume specific geometric shapes for the clusters. Here we can see some differences among the two as well. Number two, hierarchical clustering. Hierarchical clustering methods build a tree-like hierarchy of clusters by recursively merging or splitting clusters based on their similarity. Unlike DBSCAN, which do not produce a hierarchical structure of clusters, hierarchical clustering can capture nested relations between clusters. However, hierarchical clustering may be less efficient for large datasets, and the choice of linkage, for example, single linkage, complete linkage, can significantly impact the resulting clusters. And number three, density-based clustering. DBSCAN belongs to the family of density-based clustering, which also includes optex, ordering points to identify clustering structure, and HDBSCAN, hierarchical density-based spatial clustering of applications with noise, which basically is one of the improvements of DBSCAN. These methods share common principle of clustering based on the density of data points. So let's explore some of the limitations in detail. For number one, sensitivity to hyperparameters. DBSCAN's performance is sensitive to the choice of hyperparameters such as epsilon and mean points. Poorly chosen hyperparameters may result in suboptimal clustering outcomes. Number two, difficulty in handling clusters of varying densities. So dense clusters may absorb neighboring points from sparser clusters, leading to the formation of oversized clusters, while sparse clusters may be overlooked or fragmented into noise points. Number three, sensitivity to noise and outliers. DBSCAN is designed to handle noise and outliers. However, the algorithm's performance may degrade in the presence of high levels of noise or when noise points are interspersed between dense clusters. And number four, computationally intensive for large datasets. So it actually runs in around O of n log n or n square, but depending on the implementation and the choice of spatial indexing structure, it can be computationally intensive for specific datasets. And lastly, it has a bit of difficulty in identifying clusters with complex shapes in high dimensional data because DBSCAN relies on the local density information, which may lead to fragmented clusters or suboptimal cluster boundaries for datasets with intricate geometric structures. Now, although DBSCAN, as all other algorithms, has these limitations, it is widely used in various domains. For example, number one, geographic information systems for spatial data analysis, such as clustering geographical data based on proximity or density. It has been applied to tasks such as identifying hotspots of crime incidents, clustering detect regions of high activity, and segmenting satellite images to identify land use patterns. Number two, anomaly detection. DBSCAN's algorithm ability to identify noise points as outliers makes it suitable for anomaly detection tasks. It can be used to detect unusual patterns or outliers in datasets such as network intrusion detection, fraud detection in financial transactions, and detecting defects in manufacturing processes. Number three, customer segmentation and market analysis. It is often employed in customer segmentation and market analysis to identify homogeneous groups of customers based on their purchasing behavior or demographic characteristics. Number four, image segmentation and object recognition. It has already been utilized in computer vision applications for image segmentation and object recognition tasks quite a lot. It can be used to partition images into coherent regions or segments based on pixel intensities or feature similarities. So these are just a few examples of the diverse range of applications where DBSCAN has been successfully applied. Its versatility, robustness, and ability to handle noisy data and high-dimensional data makes it a valuable tool in various domains, including data mining, machine learning, and spatial analysis. Now, to conclude, DBSCAN is a powerful density-based clustering algorithm that can identify clusters of arbitrary shapes and sizes. By leveraging the density of data points, DBSCAN offers flexibility, robustness, and applicability to various real-world scenarios which are well defined. However, it is essential to understand DBSCAN's assumptions, hyperparameters, limitations, and applications to use it effectively in practice. So, thank you for attending today's lecture on DBSCAN. I hope you find it insightful and informative. The references are provided here in case you would like to hear more about DBSCAN. Until then, take care. Thank you for watching.